Okay, hello everyone. So I'm going to start with the presentation. It's called Detecting and Countering Implicit and Subtle Hate Speech Messages on Social Media. So it's basically a work that of all the time that I've been here in the Webmix team. So I hope you like it. So to begin with, a content warning. Since throughout my presentation I will be using examples that may be offensive. They don't represent the point of view of the authors, and they don't intend to offend anyone. So to start, I will define the different concepts that in which we work on. So hate speech. Hate speech is a direct attack against people based on what we call protected characteristics. It can be race, ethnicity, national origin, disability, among others. Then we have explicit hate speech, which we have a hateful part that is given directly, no? Like an insult, like a slur, as in the example in red. Then we have implicit hate speech, where the hateful part is coded through implicit devices. This can be irony, exaggeration, as again the example in red. And then subtle hate speech is a bit different. It can be either implicit or explicit. That is, the hateful part can be given directly or coded through implicit devices. But there are other constructions in the text that deviate the focus from this hateful part. So, for example, here the part underlined. No? I think it is a bit late to look after, like a circumlocution, adding more weight to the sentence. No? So to start, we built a data set because at the moment that that we carry out this project, there were no data sets available on implicit and subtle hate speech. It's normally they were focused on explicit data that is created with keywords or special tokens. So we built this data set that consisted on 4 layers. The first layer on the hate speech and non-hate speech. Then the second one for those messages which were hate speech, you add the implicit layer. Also, you add a third layer with the subtle and non-subtle. And for those which are implicit, you add the justification, no? Which was the property that was used to code them. So then in the end, we had this label distribution for the training, development, and test set, where the particularity here is that the minority class in implicit and subtle, you have an imbalance, no? So this is something that then we try to carry out to deal with this. For the implicit properties, well, these are all of them. There are a total of 18, and the ones in red are the most frequent ones, the most predominant ones. For dealing with the minority class, we applied data augmentation on the training data set. These are all the methods. I'm not going to explain like all of them, but they are very simple. So it's just as the name suggested. No? For example, if you have replace name entities, it just takes an input sentence, it takes a name entity, and it replaces for another one that is the most similar. And we created a library for this, so it can be used. Well, this is the repository, and also you can use it as a Python library. This is just an example of one of them. So in this case, it's replacing adjectives. So it takes one original sentence, it takes one of the adjectives, and it replaces for another one that is the most similar one. So while we perform this data augmentation on the training data set, and this is the label distribution, again, that we obtained for the minority classes. So the total number of messages were the ones in red for these two classes. And now this is the original distribution, the one that is highlighted in red. And then after, well, you see that at least the imbalance was less strong after the augmentation. So the ones here in red are the ones that could get, let's say, a more balanced distribution. And this is a snapshot of the data set. So we have the message ID, because we built it from different sources. So this is to be able to track it back to the original source. The text message, the source, and the 4 layers, no? The hateful one, the implicit, the subtle, and the implicit properties. Also, you have a column saying if the message is the original one or if it is augmented, and the target class that it's being attacked. So well, then for the evaluation, we tested state-of-the-art models on the task of implicit and subtle hate speech detection. So we had a 3-level classification for this: non-hate speech, explicit, implicit, and non-hate speech, non-subtle hate speech, and subtle hate speech. So here, basically, the model that performed the best without augmentation was the Berta for the implicit task. Just a minor comment that remember that if you have 3 labels, the random model is an F1 score of 1 out of 3 for each of the labels. So in this case, it was performing well for the non-hate speech and explicit hate speech classes. And then for the implicit one also was performing over the random model. And we got improvements after using augmentation in the case for HateBird. So this is the improvement we got on that class. That is the one that we're interested in detecting. For the subtle one, here models do not work well without augmentation. If you see the subtle class, well, it outperforms on the F1 score. But then as soon as we start using the augmentation strategy, for example, for back translation, we could, well, at least predict a reasonable score for this class. So for this part, we got that the most misclassified implicit properties were inference, context, sentiment, exaggeration, and extra linguistic knowledge. And in the subtle task, it was the factor of why we got these errors was more because of the word order and the circumlocution. So in the end, the contributions of this specific part, it was that models, the state-of-the-art models on the hate speech domain, they failed to detect implicit and subtle tasks because of these implicit properties: sentiment, inference, context, and irony. Then augmentation is not the ultimate solution, but it might still play a role. And also, well, we build the first benchmark for implicit and subtle, no? And these are if you want to take a look at the repository, the dataset card and the paper of this work. After this, we wanted to explore a bit more the part of the augmentation. So we thought, okay, we can still get some improvement from this part. So well, one of the things that we decided to explore is to make a generation of implicit messages which were adversarial. That is, adversarial means that that tackles or that challenges a specific hate speech detector. And so we did so by using LLMs. How we generate these messages. So first, the classic approach, when you use an LLM, you have an instruction here, and then you can use either 0-shot or few-shot. With 0-shot means that you don't provide any examples, you only have the instruction, and then you ask the LLM to generate what you asked. And then with shots, you provide examples that hold or that accomplish the instruction that you provided. So in this case, the instruction was to create additional implicit messages, and we were providing examples of the ones that we wanted. But well, the problem of this is that this strategy doesn't deal to adversarial implicit messages. You might get an implicit message, but it doesn't, it's not gonna be for sure an adversarial one. So it might be, let's say, easy for a hate speech detector to detect it. So well, something that we wanted is to somehow generate something that makes the detector fails. So then we could retrain on them. So well, we provide a variant of a beam search, which is called constrained beam search. So we're given a language model, then a classifier, a certain context from W0 to WI, and a candidate next word. Normally, LLMs work in this way. They calculate the probability of the next word given the context. So then the higher, the better for the candidate word to be selected. And then how it is selected, basically this probability is calculated for all the words in the vocabulary, and you select the top K words or the top P words that are in the list, in the vocabulary. And also you can run this in parallel. For example, you can run several, let's say, generations in parallel, which may correspond to the number of beams. So, well, this is the classical beam search, no? So here there is no constraint, but we added additional ones to this. So in this case, we added here the number 2, that basically it calculates the probability of being either non-hate speech or explicit. Then the number 3, we use by using the data set that we built, we created a lexicon of implicit tokens that are from 0 to 1, and we ask to the lexicon to find the next candidate word in the generation. And then also we wanted to constrain that the new message that is being generated, it has to be similar to the shots. So in this case, the SI correspond to the shots that you are providing in the input text. And here we are calculating the distance of the shots with respect to the new generation. So, well, why we wanted to have 2, 3, and 4? The 2, it's because we wanted to make sure that the generator, that the detector fails. So the higher the probability of number 2, it means that it's gonna be more hard to, if you provide, if this part is implicit, is an implicit hate speech message, and this number is close to 1, it means that you are failing. No, you are not being able to detect it. So the higher this number, the better for us. In the sense that it's gonna be a more adversarial. Also, the higher for 3, it means that the next word, it's more implicit. So that's a property that we want. But also at the same time, the constraint number 4, it's okay, I want that my new generation is close to the shots that I'm providing. So those are the reasons, or the intuitive reason of each of the constraints. And the problem is now is that they are separated. So we need to somehow put them all together. So one possible strategy is to multiply by each of the terms. But well, here you cannot measure how much you want to add to each of the terms. So one common strategy is to add logarithm to everything, but the logarithm of the multiplication is the sum of the logarithms. And then you can add a hyperparameter to each of the terms. So then now the constraint beam search is not only 1, but it's the sum of these 4 terms. So then you maximize the full equation here. And then you follow the same approach. You select the ones which have the top K probability. Well, in this case, it's going to be a score. It's not anymore a probability because it has more stuff, let's say, than just a probability. So, well, the whole pipeline of the generation is like this. You start with an instruction, you provide the shots, which are extracted from an implicit hate speech corpus. You can run in parallel a number of M beams, that is a number of M generations. You will have the partial output 1 to the partial output M. You calculate the probability of the next word for each of the partial outputs. Then you select the number of top K words from the language response. You will get the score of them. So this is basically the formula of the number 1. Then we calculate the scores for the constraint 2, 3, and 4. We put them all together, and then we proceed to reweight all the terms. And if we finished, we produce the output. If we didn't finish, we come back to the partial output, and we continue and repeat the process until we complete the sentence. So, well, in the end, the contribution was that with these constraints, 70.3% of the generated messages were actually implicit, and 90.7% of them beat the classifier in question. In this case, it was a hate-bird model. And then if you incrementally retrain on these messages, you improve false negative classification. So and then we proceeded to provide the repository and the paper of this. Then as a next step, we stopped in the part of the augmentation and we proceeded to then improve on the embedding representation part. So how can we improve the representation of implicit messages? So well, one strategy that we wanted to and that we consider, the hypothesis was that imagine that you have an implicit message, and well, they somehow have a stereotype or they have an implied meaning, no? So if we read this implicit message, basically the implied meaning or the stereotype is this one, that Black people are uncivilized. Okay, then there are a lot of explicit messages, normally in corpuses, that basically use the exactly same stereotype. So what happens if to all those implicit messages that have the same stereotype, we can put them together in representation space with those explicit messages that have the same implied meaning and same target group, of course. So well, if we can do that, we might, let's say, improve the classification results. So this was the hypothesis that we wanted to test. So well, we check on the literature if there was somehow a way to constrain or to add this constraint in the detectors. And there is something called contrastive learning. So how does it work this? Basically, you need to have something that is called a positive pair and a negative pair. And then you modify a loss function based on these positive and negative pairs. Positive pairs are the ones that you want to put them together, no? In the representation space, and negative pairs are the ones that you want to be farther apart. So as I was saying, we want to put together implicit messages with explicit messages that have a certain implied meaning or stereotype and the same target group. So this will correspond to positive pairs. And the negative pairs will be the other ones, no? Basically the ones that we want to just make the classification, so the hate speech and the non-hate speech ones. So well, we tested the classic state-of-the-art models, BERT and hate-BERT, on the detection task of the hate speech versus non-hate speech with and without contrastive learning. So how does it work? Basically, you have this loss function, the loss contrastive, and here you have L that represents the label pair. So this is 1 for positive pairs and 0 for negative pairs. So if it is a positive pair, basically this part of the sum gets cancelled and only considers this one. And if it is a 0, well, this part gets cancelled and then it considers this one. And S corresponds to the distance between the elements in the pairs, no? So this is the similarity between the component of the first pair and the component of the second pair. And then you sum this contrastive loss with the classical cross-entropy loss in the classification. So then in the end, the final loss that you use in the training process is the sum of the contrastive loss and the classification loss. And then in the end is the usual thing, no? So you train the models and you go on. So well, by the time some other data sets started to appear for implicit hate speech, and currently we have these 5. So the one that we built, the social bias inference corpus, the implicit hate corpus, Dynahate, and Toxygen. So these are let's say the data sets which are oriented to implicitness. Just one thing. Well, the one particularity is that ours is the only one that has subtleness. The other ones only contain implicitness. So for this specific work, we were only considering implicitness and non-subtle, just to have an alignment with all the labels between the 5 datasets. So well, this is the percentage of implicitness for each of the datasets. And here we have the comparison of the hate bird and contrastive hate bird with applying or not the method. No? So well, here we could see that there was an improvement in cross-evaluation setting. So we have for the SBIC dataset that it was performing better in the implicit hate corpus, DINA, and the dataset ICE hate. Similar for Toxigen and for and if we train with ours and we evaluated in the implicit hate corpus. So it works for some of the cases and for some other ones. Something that we also noted is that, for example, here we have the embeddings and representation of hate bird without the approach, no? And as soon as we started using the contrastive learning, so we could see that there were some the clusters. There was the clusters of the targets. They started to be more together, let's say. So probably that helped them in order to find the separation between the spaces, no? So for example, here might be the line between that separates the classes for the hate speech and the non-hate speech. So in summary, the contributions were that we cross-evaluate current state-of-the-art classifiers on these implicit benchmarks, improving the embedding representation across the different target groups in order also to improve the detection. And we preserve the efficacy of detecting hate speech labels in the new space while refining some classification in other borderline cases. And here we provide also the repository and the paper, and if you are interested in checking that. Well, after this, we started focusing on not only on detection, but also in explaining implicit messages. Basically, the motivation was to help content moderators on social media to get the real meaning of the hate speech messages. So imagine that you have here this implicit message. Well, the idea could be to have an explanation of why it is considered implicit hate speech. And then this may be useful for a content moderator in a social website that needs to check manually why the detector was given such label. And well, this is important because imagine that you are in a sensible task. You have a user that probably was banned by was labeled as hateful by the detector, and this user has, let's say, a lot of users. Sorry, a lot of followers. So well, maybe this user might be working with this with the social account. So if you let's say by mistake ban it or something, it might not be nice. Let's say so. The idea is to refine as much as possible the moderation part. So well, we wanted to test first how the joint generation between the label and the explanation, if it affects the classification performance. Then we wanted to test how the explanation were in terms of faithfulness. Then also we wanted to test in RQ3 if they could explain the implied meaning, and finally if the explanations were plausible, that is, if they could be easily understandable by humans. So these were the 4 RQs for this part. For the datasets, we relied on these 2, the implicit hate corpus and the hate check. They were a bit different to the ones that we described before, just because there was a column in these datasets that consisted with the implied statement. Basically, this implied statement, we use it for the testing. We wanted to have what we will call as gold explanations. So we really needed these implied statements for making the testing. So that's the motivation to choosing these to the specific datasets. So we had, for the implicit hate corpus, a total of 6,217 implicit hate speech messages, plus implied statement. And for the hate check, we had this amount of hate speech and this other for non-hate speech, both again with implied meaning for each test case, for each message. And we wanted to build with the implied statement what we call gold explanations. And we use it, and we build it through the following templates. Basically, a gold explanation might consist of the message is the label against the target because it implies the implied statement. So we were using these three features to build this explanation. So here is an example of how it is built, a gold explanation. No? We have the message is hateful against gay people because it contains implicit derogation that compares gay people to animals. And this other one, the message is hateful against Muslims because it implies that Muslims are overly sensitive. So for these datasets also we applied several pre-processing in order to cure the implied statements and correctly have these gold explanations. So well, then we proceeded to test the following strategies: the zero shot with a specific instruction. So given only the hateful or non-hateful text to predict, we instruct LLMs with the following prompt: given a message, label if it is hateful or not, label the target of hate, and generate an explanation of why the sentence is hateful or not. Then we proceeded with few shot, that is providing additional demonstration examples with the same instruction, and then with fine tuning. So again, it's the same instruction as the zero shot, but we were providing in the training process pairs of the prompt and the gold explanation. So we were using the gold explanation that we built as training material. This from the implicit hate corpus. And for the metrics of the evaluation, we had one set of automatic evaluation and then one set of human evaluation. For the automatic, we were using the accuracy for the detection part and the intersection over union and blue for the token level for a token level comparison between the explanations, and then for the semantic level, the BERT score. Just the BERT score is basically a BERT model that so you have the messages, you pass them to a BERT model. So you get the embeddings, and then the comparison is done by the cosine similarity. Then for human evaluation, we tested fluency, informativeness, and soundness. So fluency basically evaluates if it follows proper grammar, informativeness if it provides new information apart from the one given in the original hate speech, and soundness if it's valid and logical. No? And this is a Likert scale from 1 to 5. So here there are some examples of this is an example of a message, sorry, an explanation that has the highest score, because again, it's fluently correct. It provides several pieces of information, and these pieces of information are logical and valid. And here this is an example of a message that is not, let's say, that doesn't follow a proper grammar. It doesn't provide any information relevant to the hate speech, and well, if it doesn't provide any information, also might not count as in the sound metric. And then for faithfulness, here what we did is not only to provide the hate speech and the explanation, but we also provide the gold explanation. So the annotators needed to see this. And well, similarity was to what extent the predicted explanation mirrors the gold one in meaning. Originality, it measures whether the predicted explanation offers more than just a repetition of the input text. And context, if it provides more information besides the one in the gold one. So again, we have here a Gilbert scale from 1 to 5, except for the context, which it was only a binary score. And here again, we have an example of one that has all the scores for 5, and one that has, let's say, the lowest scores for in the human evaluation. Then, in order to answer each of the RQs, we proceeded with the following experiments. We ran an ablation study with the prompts with explanation and without explanation, these 5 LLMs, and the generation strategies that we described, and we ran and we measure them using the automatic metrics and the human evaluation ones. So we could see that with explanation, we got an increasement on the accuracy for zero shot, few shot, and fine tuning, and this increasement was also statistically significant in both datasets, no? So for the hate check and the implicit hate corpus. The only problem was that if we go deep, if we make a more fine-grained evaluation for some, let's say, functionalities, for some test cases or for some categories, taxonomies, we got an improvement, but for some others, we got a decreasement. No? For example, we noticed it when we wanted to classify non-hate speech messages. So, for example, homonym slurs, reclaim slurs, negative negation of negative statements. Then, for the automatic evaluation, basically what we notice is that few shots and fine-tune basically closely resemble to the gold explanation text, because again, you are providing examples, and well, the generation is based on those examples. So in this case, they will have a higher blue score than the one of the zero shot, and then a higher intersection over union than the one of the zero shot. But still, it preserves, let's say, while still preserving, let's say, the score of the semantic meaning. No? That's why we also included this BERT score. But in the end, if you check them manually, the different generations, they are quite good. So depending on how you want the generation to be, you might select one specific strategy for over the other one. So if you want more structured template-like generations, you will go with few shot or fine-tuning. If you want less structured ones, you will go with zero shot. Then for the human evaluation, we tested on. So we took here a total of 100 messages from the implicit derogation functionality on hate check, and 2 graded level annotators manually evaluated the triples, no? Measuring similarity, originality, and context. And we did this for GPT-4 generations. So in this case, what we noticed is that the implied meaning on these explanations were actually uncovered, and they had a proper similarity, a good similarity, originality, and context. So there was no problem with this. And it was for both datasets, for the hate check and the implicit hate corpus. And still with a high percentage of agreement and Krippendorf's alpha. But still take into account that these annotations or these metrics contain a degree of, let's say, I mean, it's not like super exactly, so it might be relative to one person or to the other one, still with annotation guidelines. No? We wanted to decrease as much as possible this, but again, there might still have some degree of disagreement. And then for the RQ, to check plausibility, we evaluated this with 25 graded level annotators on pairs of the message and the predicted explanation. So, well, 10 pairs were randomly distributed to each annotator, and they measured fluency, informativeness, and soundness. So in total, we had 250 messages, where all pairs correspond to the GPT-4 predictions. So again, here we got that the generations were highly fluent, highly informative, and sound. The only particularity that we notice is that some examples were, received low scores because, for example, for this message, gay lives are worth so much. It was considered as a non-hate speech, in the dataset, but the annotators thought that it was actually ironic, no? And they were giving low scores because of this. Okay, they were saying, okay, this explanation is wrong. It's not sound. So, well, for the contributions, we evaluate the impact of jointly predicting labels and explanation, showing it enhanced models' prediction capabilities. And we also evaluated how these explanations were in terms of automatic and human evaluation methods. So here we have the repository and the paper if you also want to take a look at it. And then we proceeded to integrate our previous contributions as part of a web tool called Peace, providing explanations and analysis for combating hate expressions. So it comprises three main functionalities: the exploratory analysis of hate speech messages characteristics, the prediction of hatefulness, and the explanation of system predictions. So the pipeline works as following. Basically, you have a user that provides an input text. This can be an implicit message. And we use a fine-tuned BERT with implicit hate speech messages to make the detection. So it may provide that it is hateful with a certain degree of probability. And then this probability and label was inserted in the prompt of the explanation in order to make the final explanation. So in this case, the text, we insert the message given by the user, has been labeled as hateful with a probability given by the detector. Generate an explanation of why the text is indeed hateful. And so then we proceed to get the explanation here. And then if you want, you also can make an exploration on the implicit hate data that we used to make the different analysis. No? So here we let the users decide what are the filter decisions that they want to carry out. So in order to test this, first we focused on the detection part. So we check on different detectors like BERT, hate BERT, contrastive BERT, and contrastive hate BERT, that the ones that we did before, and Mistral and Alpaca, and we check how they were in only classification for all the 5 datasets that we described before. And so, well, we could see that actually the one that performed the best in the implicit class was the BERT model, at least the one that was consistent Also, Mistral performed very well in some of the cases, but still the ones that we were interested were the implicit messages. So we consider BERT as the detector. No? So this was to prove that, okay, adding the detector in the pipeline makes sense. It can improve the detection part. Then proceed to make the explanation. But if you start from the base that the prediction is wrong, well, your explanation is going to be wrong. So, well, then if we combine the BERT and the Mistral model, we could see that actually it is highly fluent and it provides more informative explanations than the one without, more persuasive, and sound. And all of these cases were calculated. We calculated the statistical significance. So we got an improvement by adding the detector. Well, then we proceeded to have the repository, the paper, and here the demos. I will just show it quickly. So this is just the interface. I will go with the explanation part. Basically here, what we have is the input text that can be inserted by the user. This is just the template example. You click on the explain text. So here, basically, this text message is given to the BERT model that was fine-tuned on implicit messages. It makes the prediction, obtaining the label and the probability, and then it proceeds to generate the explanation. So here, in this case, it's saying the inserted text is hateful with a probability of 0.767. And the text is considered hateful due to its use of generalization and stereotypes. It implies that all black politicians are in power due to tolerated crime within the black community, and that the white people only care about safety and good governance. This perpetuates harmful racial stereotypes and fuels division between different racial groups. So well, then also during demo time, we also have different messages in order to test the different explanations. And if you want to play, you can go to the demo section of the Tracia. Basically here, you have all the demos. And here it appears the one that we have. So you can access the demo and make some generations if you're interested. So this I will go back to the presentation. So now the last part, the hate speech countering. Here it was, we changed from the part of detection and explanation. So then we started focusing on the generating counter speech. And in particular, we focus on two research questions. Do safety guardrails affect the quality of the generated counter speech? And if focusing on a specific component of the hate speech is better, no? So here we have an example. Imagine that we have this hate speech message. So here, what we did is basically obtaining the argument components of the hate speech. So in this case, the first part is the conclusion, is the premise 2, and the premise 1. And also we obtain the implied statement. And these premises and conclusion were annotated with if they were actually hateful or not, and which of these arguments was considered the weakest. For us, the weakest argument was the one that could be attacked the most, no? The one that you could provide more arguments to counter-argue, let's say, the statement. And we tested these different generations. We got models with guardrails and no guardrails, the specific parts to attack, the implied statement, the hate, and the weak, and also without any part to attack. And then we had this fourth, and then we have different metrics for human evaluating this. No? The relevance, that measures how relevant is the counter speech to the hate speech message in terms of topic and target of hate. So the annotators basically had this table and they could follow it to make the evaluation. Suitableness, basically how much is the style of the hate speech suitable, if it is polite and non-hateful, if it attacks the message and not the hater, etc. So again, the annotators need to follow the different scores and the table. Informativeness, again, so you have different pieces of information, and the annotators need to focus on if they were actually, well, how many pieces of information they were, and if they were actually factually correct or not. And cogency, same, you had different pieces or different arguments, so the annotators need to check the number of arguments that the counter speech had, and if these arguments were actually sound or not. So in the end, the home message was that the absence of guardrails indeed has a positive effect on the cogency without hindering the safety. And also attacking the implied statement and the hateful elements results in better counter speech. So how we check this? Basically here, this row corresponds to the model with guardrails and this other row without it. So we could see that here you get counter speeches, which are higher in terms of cogency with respect to the without guardrails. and they are statistically significant. And here we have SAP, which is a metric for safeness. So it is indicating that if you remove the guardrails, still you get counter speeches which are, I mean, safe. No. Also checked by the suitableness, because suitableness again corresponded to this aspect. And here, if you compared the different evaluations in terms of the parts to attack, we could see that the one with implied statements has a higher cogency, informativeness, and suitableness, and also well the relevance with respect to the base one. So well, we could discover these two aspects. Again, removing the guardrails, it improves in the cogency, and if you focus on different arguments to make the generations, well, you get again more cogency and safe answers. So this is an example just to have an idea. With guardrails, you normally get counter speeches which are like kind of vague. The statement is harmful and unethical as it dehumanizes Black people and suggests that they have no inherent value. It is important to challenge such thinking and strive towards creating a more just and equitable society. So here, I mean, it sounds nice, but it doesn't tell you a lot. While if you remove the guardrails, maybe it doesn't sound as nice as it should be, but it's not unpolite. So in this case, it's like it goes very directly. This argument fails to acknowledge the complexity of human societies. It also assumes that civilization is the only way to be human and ignores the contribution of people from diverse backgrounds. No one should be deprived of their dignity based on their race or cultural backgrounds. So again, it's not unpolite. Maybe this one sounds more empathic, but still this one is more like cogent and informative than the other one. So again, if you want to check the repository and the paper, here they are the links. So as current and future work, basically now we are working on three lines of research. One is we are using argumentative structure on hate speech and counter speech messages to generate and obtain good quality counter speech. And we focus on conversations of the white supremacy forum. In particular, there is a section in this forum that is called Opposite View. That is very interesting, and well, we are trying to make a scrapping of that and see if we could actually use it to make an analysis on that, on real data. Then we are currently extending the NLDB paper, experimenting with context-based and argument-based generated explanations. So for the moment, we were experimenting with zero shot, few shot, and fine-tuning. Well, we wanted to discuss, similar to the counter speech part, what happens if we use an argument-based generation or a context-based generation, for example, adding not only the label and the probability, but something else like the most relevant tokens or adding information from the detector. And also, well, we also plan to continue working on identifying implicit and subtle messages by proposing different means of currently detecting well the misclassified implicit properties that we mentioned before. And that's it. These are the list of publications. And if you have any questions, I'm happy to.
Thank you very much.